A shortwave delta loop, tilted and asymmetric. We will find out how the radiation properties are affected. Loops are popular because they are picking up less noise than other antennas. Shortwave radio amateurs are reporting that, and here on the channel we carried out experiments showing less intermodulation with loops. In one of the last videos we investigated a horizontal full-wave loop at low antenna heights. Today we are analyzing a delta loop adapted to unfavorable local constraints. As a loop antenna's impedance is usually hundreds of ohms, you need a suitable matching network. Interestingly, you can dimension the delta loop to exactly 50 ohms impedance. Its setup is pretty simple and therefore suitable for use on the go. I came across this by chance. Clever people figured it out long before me. A 37-degree angle between wires B and C yields the desired 50 ohms impedance. We can assume that the proven concept is working fine as long as you set up the antenna vertically with the exact dimensions. Now the question is, what compromises can we make in terms of antenna height and symmetry? Let's get to the dimensioning. The length of the circumference is determined by the operating frequency. We make sure that the height of the feed point above ground is 1.5 meters, for example. A factor A is applied to achieve the exact electrical length. 1.061 applies to a 2 to 3 mm wire in the shortwave range. In case of 2 mm wire applied at 8066 MHz, a value of 1.1 is appropriate. At higher frequencies, the tool gives us a slightly larger angle instead of 37 degrees, the reason we will explain later. We are getting the length for wires A, B and C, as well as the height above ground at which we need to mount wire A. The yellow numbers are giving the lengths in multiples of the wavelength. Next I will show antenna dimensions for a number of frequencies. You can stop the video to read the values that you are interested in. First, we look at the amateur radio bands, 160 meter, 80 meter, 40 meter and so on, up to the 23 centimeter band. And then we are computing designs for all worldwide LoRa frequencies, 169 MHz, 433 MHz, 868 MHz and 915 MHz. And finally, there is the dimensions for Wi-Fi frequencies 2.4 GHz and 5 GHz. Now let's assume we want to build the antenna vertically for the 40 meter ham radio band. We would need to put the element A on a height of 18 meters, which is simply not possible in many cases. However, it is realistic to go to 12 meters with the help of a building and a tree. For that height constraint, we have to construct the loop at an angle. Keeping the feed point at 1.5 meters above ground, we get 41 degrees inclination of the antenna against ground. What effect on the radiation properties can we expect? We are using the vertical delta loop as a reference for our investigations. At resonance frequency, we get 2 maxima and 2 minima in the current distribution, as expected. Blue color means high current and low electric field strength, white means low current and high electric field strength. As on the lower antenna part, the electrical field strength is rather weak, the influence of ground to the impedance is bearable. It's running very nicely through the matching point in the Smith diagram, and the VSWR is ideal at center frequency. The azimuth diagram, also called horizontal radiation pattern, has two main lobes at horizontal polarization. The main beam direction is perpendicular to the loop's plane. The vertical polarization forms two main lobes in the loop's plane that are about 13 dB weaker. The elevation of the main lobes is 37 degrees. The three-dimensional radiation pattern gives us the complete overview: the horizontal polarization, the vertical polarization, and the total radiation. Tilting the antenna from 18 meters to 12 meters, the current distribution on the antenna hardly seems to change. The impedance remains basically the same. The resonance frequency is slightly shifted downwards by about 50 kHz. The antenna radiates about 1 dB more in the direction of the tilt than in the opposite direction, but the gain is dropping from 4.62 to 1.45 dB. We are losing 3.17 dB of gain compared to the vertical construction. The vertical polarization seems stronger in comparison only. The absolute value is also lower. The antenna elevation diagram, also known as vertical radiation pattern, is showing that the tilted antenna radiates more energy to the sky in comparison. And here are the corresponding investigations on the 3D radiation characteristics: the horizontal polarization, the vertical polarization, and the total radiation. In the next step, we are analyzing an asymmetric arrangement where the elements B and C are different. We are gradually moving the feed point by 5 meters to the right. The current distribution remains the same along the circumference, but it is shifted according to the asymmetry. The impedance remains basically similar, but the resonance frequency is shifting downwards. The azimuth diagram rotates about 15 degrees counterclockwise, corresponding to the current's distribution. The elevation diagram remains almost the same. It just shows a growing vertical polarization, which is due to the rotation of the diagram. The 37-degree delta loop actually has an impedance of exactly 50 ohms at fundamental frequency. A slanted and asymmetrical setup has little effect on the antenna impedance. The shift in the resonance frequency can be compensated by shortening the wire elements. You could take advantage from slightly turning the azimuth diagram to your desired direction. A low antenna height is lowering horizontal gain, an effect appearing with every shortwave antenna. In case your local conditions are not allowing for better, a tilted and asymmetric delta loop is absolutely making sense. We will build the delta loop for 866 MHz to compare it with other antennas. Now stay tuned and don't forget to support the channel. See you soon in the coming episodes.